Today we're going to learn about a kind of relationship called the direct variations. Now I want you to write this down somewhere in your book. All right, everybody write this. Direct variation equals linear and proportional. Direct variation equals linear and proportional. The reason I'm explaining this is because we've already talked about what it means to be linear and proportional, and you guys have done a good job. One of the things we've realized is linear and proportional, or direct variation, if we graph it, we end up with a line that goes straight through the origin, or 0, 0, as you see here in the example. Another thing we realize is we can take any one of the coordinate pairs and set them up as a ratio, and they should all equal each other. So, if I take a y value and I put it over an x value, I'm going to get this number, and for right now we're going to call that number m. And what we realize is I can look at the next point, and the next point I can take the y and put it over an x, and I'm going to get the same answer. Because when something is proportional, all the different coordinate pairs, when I take the y and divide by the x, it's going to end up equaling the same thing. Okay? Well, people have realized this. Wait a minute. So it keeps on equaling the same thing, and they've come up with this equation. And they've said, well, y over x equals m is the same really as y equals m times x. Right? Because if I multiply both sides by x over here, that's what I end up with. Y equals mx. So it's kind of a nice, nifty little equation. Right? So m is what we call a constant. In this case, it's called a constant of variation. It's also called a constant of proportionality. And basically, it is the slope. It is the slope. It is the constant rate of change. And with a direct variation, because our line goes through the origin, it is also the unit rate. So when we have a direct variation, the unit rate, the slope, the constant rate of change are all the same thing. And that can be handy to us when we are trying to solve problems. So the difference is we've used graphs, we've used tables. Now we're going to be introducing the use of an equation. Let's look at an example. If you look at example 1, on page 190, you have a girl named Robin who is babysitting. And the key word in this paragraph is it says, the amount of money Robin earns while babysitting varies directly. Okay? It varies directly. So those two words tell us a lot. Those two words tell us that this is a direct variation, which means it's linear, which means it's proportional. Okay? It's linear and proportional. So we know that it's going to go through the origin, and we know that every single one of the points on this line, when we do y over x, is going to be the same as all the other points. All right, so what are we trying to do? We want to know how much she earns per hour. When you hear a rate that says per hour or per one unit, what do we call that? Anyone remember? Per one unit. Oh, there it is. We call it a unit rate. All right? So it's great to know it's great to know that I can drink 5 Cokes in 1 hour. You can. Well, how long does it take me to drink 1 Coke? Well, 12 minutes. Okay? It's good to know the unit rate is more helpful. Don't tell me how many miles per 3 hours your car goes. Tell me how many miles per hour it goes. It's a unit rate. So in this situation, we're asking for a unit rate. Now remember what I said earlier. With a direct variation, the unit rate, the slope and the constant rate of change are all the same thing. So if we want to know per hour, there's a couple different ways we can do it. Number one, we can find the slope, find the constant rate of change. Okay, so here we have some points. This looks like a good point. We have the point 215. We have the point, she also says she worked for 3 hours and earned $22.50, and she worked for 4 hours and earned $30. So now, like I said, in a direct variation, we can do change over y. We can do change in y over change over x. But because we know in a direct variation that all these points are proportional, we can take one of them and just do the y divided by x. So I can take 15 divided by 2, and I get 7.5, and I know that Robin earns $7.50 an hour. Another way I could look at it is I could try to figure it out on a graph. Here's 1 hour. So what's this point right here? Halfway between 5 and 10? Looks like 7.5. I could do change in y over change in x. I could go up and over and have an increase of 15 and a rise of 15 and a run of 2, and that equals 750 as well. I could take, there's so many different ways I can do this, but the bottom line is I just need to get a y value and divide it by an x value, and in a direct variation, that's my slope. Okay, let's look at one more. So remember, direct variation, linear, proportional. Okay, how can you know that this example is a direct variation? It's a straight line, which means it's linear. Yes, ma'am. All right, Savannah says it goes through the origin. So if it goes through the origin, it means it's proportional. And what did we say in the last slide? Direct variation equals linear proportional. So we know this is proportional. And on a direct variation, if I want to find the slope, the unit rate, the constant rate of change, it's all the same thing. So in this example, we want to know how much this person earns per hour. Well, we can take this coordinate pair here, which is 440, turn that into a y over x, and figure out what m, our slope, is. So y is 40, x is 4, so we know that this person earns $10 an hour, okay? So y divided by x gets you your slope, your constant rate of change, or your unit rate. Go ahead and try the first got it at the bottom of page 190. The first got it at the bottom of page 190.